Welcome everyone to this presentation. This is Asif Khan from Georgia Tech. It's my great pleasure to give this talk to the distinguished audience at the International Symposium of VLSI, and I apologize for not being able to be present physically at the conference. So I'd like to thank the organizers for accommodating this online presentation. So my talk today is about a new device technology called the ferroelectric transistors, and I will talk about how this device technology can enable alternative non-von Neumann computing models. So in this talk I will mostly stick to the device level aspects of ferroelectric transistors and then show how the unique properties can be utilized in interesting manners for these applications. So I hope that my talk will complement the next two talks in this session. So with that, let's get started. So computing today is dominated by data intensive applications thanks to the rise of machine learning AI, and we are generating these massive amounts of data by our social media, by the videos that we watch, the analysis of our DNA, or even scientific experiments such as the Large Hadron Collider or the observation of the universe. And as we are handling these amounts of data, we are increasingly realizing that we need to depart from the von Neumann architectures. In the von Neumann computing models, we make a clear distinction, both logically and physically, between the computation or the logic units and the memory units. And for data abundant applications, it is being seen that most of the energy is being dissipated in moving the data between the logic and the different levels in the memory hierarchy. So over the last couple of years, there has been significant interest into new types of computing models, non-Neumann computing models. We have seen different in-memory computation architectures, oscillatory neural networks, spiking neural networks, and so on and so forth. And even more so, we are looking at computing systems that are inspired by the fundamental principles of operation of the biological brains and its functional units such as the neurons and synapses. Parallelly, over the last couple of years, a number of new device technologies have emerged. So the examples of such device technologies include spin transfer torque, magnetic random access memories, phase change memories, resistive RAMs, conductive bridge RAMs, ferroelectric memories, and metal insulator devices. And it might, interestingly, it might be the case that these emerging technologies might be more appropriate for implementing different non-von Neumann architectures. So as I said, my talk is about these ferroelectric devices, and what I will do in the next couple of slides is show you how the ferroelectric memory device works, what their interesting properties are, and then finally I'll give an example of an alternative computing substrate that can be implemented by this ferroelectric device technology. Alright, so now what are these ferroelectric materials? So ferroelectric materials are essentially insulators that have a spontaneous polarization. So for example, if I look at a unit cell of a ferroelectric material, you will see that the central atom over here is not at the center of symmetry of the unit cell, rather slightly off-centered. And as a result, the ferroelectric materials can show a dipole moment even when there is no applied electric field. For example, in this case, the atom is slightly shifted upwards. In this case, it's downwards. So the polarization direction in the two cases are in two different directions. So as they're insulators, you can make capacitors, and if you then measure the charge voltage characteristics, you will get a hysteresis in this charge voltage characteristics. Now what you can do is you can include a ferroelectric material in the gated oxide stack of a transistor structure, and the resulting structure is what we call the ferroelectric transistors. And what is interesting is that because it has two bistable states with two different direction of the polarization, This polarization direction essentially changes the threshold voltage of the transistor. For example, if the polarization is pointing downwards, the threshold voltage will be low, and as a result you will get this branch, the upper branch of the current voltage characteristics of the transistor. On the other hand, if the polarization is pointing upward direction, it will be in a high threshold voltage state, and in that case you will get current voltage characteristics that corresponds to the lower branch of this curve. And essentially, if you sweep the gate voltage, you will get a hysteresis in the current voltage characteristics of this device. And if you look at the gate voltage of 0, you can get two stable states, and these two stable states can be the two non-volatile memory states of the device. So essentially, ferroelectric transistor has been mainly considered as a non-volatile memory device technology, and the data is encoded in its threshold voltage. So my purpose in this talk is not to show the memory application of the ferroelectric transistors. Rather, I will show that this device technology can also implement a non-von Neumann computing model based on coupled oscillatory systems. So what is a coupled oscillatory system? So now in physics you have seen many times the example of pendulums. So say you have two pendulums over here, which each of them has a different oscillation frequency. But what is interesting is that if you couple these two oscillators, and if the oscillating frequency, the fundamental frequency each of the pendulums is close by, then in certain cases these oscillations can get coupled. Now, why is this coupled oscillatory system interesting? Now, over the years it has been shown that the synchronization dynamics of a coupled oscillator system can be utilized to solve different classes of computationally hard problems such as associated memory, pattern recognition, or even combinatorial optimization. And it is also interesting that actually in biological brains there are evidence that the way the brain works, the learning of brain or the computation models quite often resemble that of a coupled oscillatory system, where the thalamus works as a forcing input and the cortex acts as a system of coupled oscillators. So what we are showing here is that a ferroelectric transistor can be utilized to make oscillators, and when they are coupled through capacitors, they can show interesting synchronization dynamics. Alright, so how do we make an oscillator out of a ferroelectric transistor? So I'm here showing a simple diagram of a ferroelectric oscillator circuit where you have the transistor over here, and then on the source end of the circuit you have a resistor and capacitor which forms a feedback network. Alright, so I'll quickly go over the operating dynamics of a ferroelectric oscillator. So here what I'm showing here is the current voltage characteristics of a ferroelectric transistor, where the x-axis is the source voltage and the y-axis is the current. And then we are plotting the load line, which is the load line corresponding to the resistance. Alright, so this was published last year in IEEE Electron Devices Letters. So let's get started. Let's try to look at how the dynamics of the oscillator is. So initially, when we first start power up the circuit, the operating point is over here, and as a result a current flows through the transistor and charges up the capacitor, and as the capacitor charges up, the source voltage increases, and that's how the voltage increases until this point. And as soon as it goes to this point, then the operating point goes down to the B level. And the reason it goes through a transition like this is because there are no stable state in this hysteretic jump section of the current voltage characteristics. And then when you reach this point, then the capacitor again starts discharging through this resistor, and as a result the voltage across the capacitor will start decreasing. And then when it reaches this point C over here, then the operating point of the transistor again jumps back up to this point over here, and then again the capacitor starts charging up. And if you design the circuit properly, this oscillation will keep on repeating like this, and as a result you will get a sustained oscillation in this circuit. But it is important that you choose the value of the resistor properly. Alright, so now what is interesting is that you can control the oscillation by controlling the voltage that you apply at the gate of the ferroelectric transistor. For example, in this particular case, for 300 millivolts of voltage, you get this oscillation over here shown in the black. On the other hand, if you change the voltage to 220 millivolts, you can change the frequency to another value over here. And on the other hand, you can also stop the oscillation if you increase the voltage to some other values. So essentially you can change the oscillation frequency or even control or stop the oscillations in the circuit by changing the gate voltage. And this is how the simulated characteristics looks like for an oscillator. Now it is interesting in that in the previous slides we had a resistor over here, and if you replace it with another transistor, you can also have another control for this oscillator circuit. Alright, so moving on, let's see now what happens if you have a system of oscillators connected through a coupling capacitor. So in this case we have this oscillator 1 over here and oscillator 2 over here, which are connected by this capacitor CC, and now we use the gate voltage of each of the transistors to control the oscillations. So now in the first case, the two voltages at the ferroelectric FET gate terminal are close to each other, and in this case we see that the oscillations in the two outputs are synchronized. On the other hand, when the two gate voltages are separated by a larger amount, then the oscillations of the two oscillators are not synchronized. They are unsynchronized in this case. Now in both cases the coupling capacitor value is 2 picofarads. On the other hand, if we increase the coupling capacitance to 25 picofarads, in this case we see that even when they are largely separated, their oscillations are now synchronized. In the previous case they were not synchronized. So essentially we see that it has this distinct synchronization dynamics for a coupled oscillatory system. These ferroelectric oscillators, they show the distinct synchronization dynamics that are observed in general in coupled oscillatory systems, and essentially these oscillations can be utilized for solving different kind of computational problems. Now the basic structure of the oscillator can be utilized to make integrate and fire neurons. So those kinds of neurons can be useful for spiking neural networks. So in this case, the way to get this neuron structure, the way we modify it is to add resistor capacitor networks to the input of the transistors. So for example, this terminal over here can work as an excitatory input. On the other hand, the input terminal to the ferroelectric FET can be utilized as an inhibitory input for the neuron. So essentially this slide over here shows a family of neuromorphic circuit primitives that can be implemented using ferroelectric FETs. So in this talk we only talked about the coupled oscillatory systems and neurons. So it can also be shown that the same transistor structure can be utilized to show synaptic dynamics. It can be utilized to implement the vector matrix multiplier structures for deep neural networks or even non-volatile finite state machines. So I believe Dr. Lee will show some other interesting characteristics that you can get out of these ferroelectric devices. Alright, so this brings me to the last part of the talk, and in this part I'll try to give a global overview of the interesting and the unique properties of the ferroelectric transistors. So essentially a ferroelectric oxide has many interesting properties, a very rich range of dynamical properties. For example, hysteresis and non-volatility. So this is what we saw in the previous slides. And then it also has interesting properties such as plasticity and stochasticity. Now in the ferroelectric FET, essentially we integrate the oxide into the gate oxide stack, and in doing so we couple all these in the properties of ferroelectric oxide to the drain current of the device, and in doing so we get a 3-terminal transistor device which has all the properties of the ferroelectric oxide that is reflected in the current voltage characteristics, and essentially we get a neuromorphic transistor which has an intrinsic gain. Now why is it interesting and important? It's important because most of the emerging devices are 2-terminal which do not have an intrinsic gain. On the other hand, in a ferroelectric transistor, because of its 3-terminal transistor structure and its intrinsic gain, we have a much larger design space for circuit primitives where all these interesting properties can be utilized for alternative computing models in a very compact manner. And that's essentially the most important feature of ferroelectric FETs for these alternative computing applications. So for example, over here I'm showing 2 different kind of systems. For example, the neurodynamical system or the neuro-oscillatory system that we talked about in this slide, in this talk, where you use ferroelectrics for coupled oscillations. On the other hand, we can use the same ferroelectric FET to design synaptic systems which can show long-term potentiation and short-term plasticity. The same transistor but in a different circuit configuration can give you 2 different kind of functional behavior from a circuit perspective, and that's one of the most important things about the ferroelectric transistors. Alright, the work shown here was performed by my student Zheng Wang, and I also acknowledge the funding agencies, the National Science Foundation, the Semiconductor Research Corporation, and the JUMP program. And with that, I invite questions and comments.